Don't forget to bring them out and do all three.
That's where I was.
Because he's
Yeah, I've already like
yesterday, I was so confused, so it literally like helped me write it out. So
Yeah. Oh, yes, I did say you guys could work on them until like, yeah. But I will take them now if you want. Thank you.
Did you do the whole thing?
I have work.
Mm. So yes, the bonus project is worth somewhere between 0 and 1,000 points. We're not really sure exactly, but
Yeah.
I refuse to answer. But anyway, let us begin with a word of prayer. Heavenly Father, we thank you for this day, and I thank you for this class. Just ask you bless this time today. Help us to use the time wisely to review for the final. Lord, in your name I pray, Lord Jesus. Amen. So do you guys have any questions about anything in particular? Yep.
First problem is beta. I couldn't tell whether it was orbitals because it didn't have a Z in it anywhere.
Yes, about the bonus project? What's that? I mean, I guess you can, but I mean, let's see here. Yeah, there's just no Z. That's fine. Like you mean the beta? Yeah, so it would be kind of like a vector field that's missing a component. You know, like you could have 0. So like is that? I think like now that I'm looking at it, we pretty much did problem 5 in class. And problem 6 I think we did in class. And then I think I might have done problem 7 in class. Problem 8, it's kind of like, I'm not sure if the question, I mean, so for problem 8, if you calculate d alpha and you get what? If you calculate d alpha in problem 8 and you get non-zero, then what's the answer? Like if the exterior derivative of the form is not 0, then it can't be exact. There can't be another one that is a potential form for that form. Anyway, let me go back, way back, to the start of the course and ask you if you know how to solve a problem. How about this one? You've got a plane, right? And suppose that plane has the points 3, 0, 0, 0, 2, 0, and 0, 0, 0, 2. And, I don't know, 0, 8, 0. And then my question is, which point on the given, which point on the plane which contains these 3 given points is closest, let's say, to the point, let us say 10, 20, 30. All right, so how do you find the closest point? So where would you guys start if I was to say put this problem on the final?
Find the normal.
The normal to the, find the normal to the plane? Okay, how would we do that?
I would find the vectors between the 3 points, 2 vectors.
Which 2 vectors specifically would you want to do?
0, 0, 2 to 3, 0, 0.
Uh-huh.
And 0, 0, 2 to 0, 8, 0.
Sounds like a good idea. Let me call those A and B. All right, so A is equal to what? Let me write it out just to, as a means of getting partial credit if I make a mistake. And B. It's often where I make a mistake is like this when I don't write this down. Sometimes it gets me in trouble. But yeah, this is what we say is 3, 0, minus 2, and 0, 8, minus 2. So those vectors are both, those are tangent to the plane in question, right? Those are tangent to this plane. And so we can calculate the cross product. All right, let's see here. 16, 6, 24. Now, I could be wrong, so I checked my work. 3 times 16 is 48. 48 minus 48 is 0. Good. And 8 times 6 is 48 minus 48, 0. Good. That vector is perpendicular to both A and B. So either I'm fantastically unlucky and correct on both dot products being 0. Like if both dot products are 0 and I have the wrong answer, it means I've got a scalar multiple of the answer. That's so fantastically impossible. For a miscalculated cross product, it's practically irrelevant. So that's the right one. That's the normal to the plane. So we have, pick whatever base point you like. I guess I like x minus 3. So I've got like 16 times x minus 3 plus 6y plus 24z equals to 0. So this is the equation of the plane. That's a good question on its own, right? And so how would you then, great, now we found the normal, how do we find the closest point? What do we do? Yeah.
We know that the closest point is, if you make a vector from the closest point to your point, that's going to be normal to the plane.
Right.
So you can find a multiple of the normal that intersects that plane with system equations.
So you're saying, excuse me, goodness gracious. Basically, it's geometrically evident that the closest point must follow the normal line, so we can look at a scalar multiple of the normal to find the equation there, right? Let's see. Yeah, so what I agree with you, but excuse me, a simple way to do that is just to parameterize a normal line through the point, because we know that the normal line has to go through the point. So if I think about this line, you know, if I think about the line with direction vector of the normal, that line has to intersect the plane at the point we're interested in. But I also know a point on the line, right? So I can write down R of t is like, 10, 20, 30 plus t times, what's the direction vector to the normal line? Well, apparently 16, 6, 24, right? While I'm closing the door, what are the other 2 ways we learned to solve this problem this semester? Do you remember? Actually, maybe 3 ways. Lagrange multipliers, right? And Lagrange multipliers is going to give us exactly the equation that, like Sam was suggesting, right? Like the Lagrange multipliers basically spits back at you. Look for a multiple of the normal vector. I'm pretty sure that's what it does. The other method early on, we used like picking a point, another point, and then specifically like projecting the directed line segment onto the to the normal part and so forth, and like using concrete projections of specific vectors with respect to the geometry in play. We could do it that way. I think that's, I'd like to, I feel like that's where I achieved maximal confusion in this course for most of you. Like when we did that, you're like, what is going on? And some of you, it got better. Let's see here. See here, others left. See here, so 10 plus 16t, 20 plus, but I think after the dust settles, I think this is the easiest way. If I come across this problem, like on a math subject test or something, this is the way I do it. It's just fastest. Now those are the equations, so that's the equations for the normal line. This is my x, this is my y, this is my z, so plug them in. And we get what, like 16 times, what you got here, x minus 3 is 7 plus 16t plus 6 times 20 plus 6t plus 24 times 30 plus 24t, all of that's equal to 0. But hey, we can solve for t, right? Let's see here. We got what? 16 times 16 plus 36 plus 24 squared. Yowzers. 868 t is equal to what? 16 times 7 plus 120 plus 24 times 30 minus 952. It's kind of funny. Everything is positive here. Oh well. And so my t is what? Minus 952 divided by 868. So my picture is obviously wrong, right? What does this mean?
Something past the plane of another negative.
Yeah, is that right?
Yes.
Oh yeah, yeah, okay.
Your normal point's the same.
Yes, so the normal's pointing away, so we have to go back from, this is t equals to 0 in our equation, right? Thank you. So that means we go back about -1 actually, right? So you're exciting as this is minus 34 over 31 for t. And so in short, r of minus 34 over 31, which is specifically, you know, 10, 20, 30 minus 34 over 31 times the normal 16, 6, 24. There you go, that's the closest point. I don't really care about the details past that point there. That should be enough to make sure everybody understands what I'm doing. Any questions? What's the area of that triangle? Anybody? Can you calculate the area of this triangle? You're like, well, that's a right triangle, I think, so I could just do like 1/2 base times height. No? I think it is though, like this. I believe that's a right angle there. I mean, we could check. Is A dot B 0? Ooh, it is not. That is not a right. That's not a right angle.
You lift that point off the plane eventually.
Yeah. Yeah. So, you know, proof by deceiving picture is not a proof, right? So if you want to check if there's a right angle, take a dot product of two vectors that are at the vertex. No problem though. What's the area of this triangle? Can you guys tell me? This is something that I often put on like page 1 of the final. Yep.
The area of the, or half the magnitude of the cross product.
Right. So the area, exactly. The area of this is 1/2 the magnitude of A cross B. Now the area of the parallelogram, like if I was to extend like this, right? The area of the area of the parallelogram is just the magnitude of A cross B. We know that, right? So half of the area of the parallelogram is the area of the triangle. So you just take half of that magnitude. What is the magnitude? Well, it's 1/2 of the square root of 16 squared plus 6 squared plus 24 squared. I don't really care what that is. The point is, there you go. That's the area of the triangle. Yeah. Although I do care on the final. Like, don't leave stuff unsimplified, please. Right? Like, I don't want the answer like this. I would like a square root of a number, you know. You can leave the half out front. I don't care about that. But I would like squares added together when there's something like this. Let's see here. Any other questions? Any questions, actually? All right. Example 2. Another thing you guys are probably a little rusty on. What if I'm like, here's vector A, is 3, 7, minus 11, and I've got, you know, a vector b up here, which is, let's say, 1, 2, 8, and I want to calculate the projection of b onto A. What's the projection of the vector b into the A direction? In other words, can you find a vector which is parallel to A and another vector which is perpendicular to A, right? So let's say the v1 and v2. Can you find v1 parallel to A and v2 perpendicular to A such that b is equal to v1 plus v2, right? If I ask you to do that, could you do it? You should be able to do this, all right? At the start of this course, this was kind of the higher end of understanding, right? Like this is separating the A's from the B's, but by the end of the course, I would hope enough time has passed that we all understand this. And so the projection of A onto B is in the A direction. So this is going to be the V1. What's V2? I call it the orthogonal piece. But specifically, it's just B minus the projection. In other words, it's kind of self-serving here. It's just B minus V1. So of course, B is equal to V1 plus V2. It's kind of silly, right? But what's not silly is it is in fact perpendicular. So what's the formula for the projection? Right, like there's dot product. Like yeah, there's two major formulas I sold you guys on. The one is you just go, okay, you go A dot B hat, and you put it in the B hat direction, all right? But specifically what that works out to, it's the same as saying A dot B over B dot B in the B direction. Oh, my bad. What have I done? Yeah, so I did it exactly backwards, right? So everything I wrote there is entirely wrong. We need to flip the role here. We're going in the A direction, so we're supposed to do B dot A hat. There we go. So this works out almost the same. It's just instead of having, we have A dot A dividing and multiply by A. So it should be in the A direction, like I said. All right, so what are those dot products? A dot B is what? 3 plus 14 minus 88. A dot A is 9 plus 49 plus 121. All of that goes in the 3, 7, minus 11 direction. All right. I think I'm just going to stop here. I don't want to like burn all of class time on doing the arithmetic of these things. I just want to remind you how we could do this. Is this enough? So I mean, I would strongly advise getting a calculator and, you know, crunching the numbers and such, but I can go on if you need me to. Nobody? All right, so let's see here. So what else can I ask you? Oh, example 3. Find the length 7 in A direction. How would you do that? Now, if you're Emily, you'll write down an equation and do algebra, as it gives you great joy, as algebra is your happy place. But if you're more geometrically inclined, you should go, oh, well, that makes V just 7A hat. That's what that is. If a hat goes in the direction of a, you want length 7. Well, a is a unit vector, so if we have magnitude times a unit vector, well, I mean, any number times the unit vector is its magnitude. That number is the magnitude. So 7 is the magnitude. And a hat, well, a hat is just, 7 divided by the square root of 9 plus 49 plus 121, whatever that is. And my a vector was 3, 7, minus 11. Which gives me what, like 130, 170, 179. So like 7 over the square root, 179, I think. 3, 7, minus 11. And that's a completely legitimate way to write an answer for something like that. It is acceptable in this course to express your answer as like a scalar multiple times a vector. I don't expect you necessarily to take that number and multiply through, right? That doesn't make the answer better, it just makes it cluttered, right? Being able to factor a number out is actually really nice. Does that make sense? Yes, no, maybe so. Another example, a blast from the past here. How about this? If I've got f of x, y, z equal to e to the xy plus z cubed minus y squared, and I want to find max, min rates of change at the point, let's say 0, 1, 2. How would you do it? I mean, what am I even talking about, max rates of change? How will we calculate the rate of change of a function of several variables? What do we do?
Like the maximum directional derivative?
Find the maximum directional derivative? That's right, yeah. That's how we calculate the change of a function of several variables at a point. We calculate the directional derivative. Absolutely. So what is that? Well, let me just remind you formally. The directional derivative at the point P of f in the u hat direction is, actually that was not my notation, was it? I put the u hat down here, and I put the p up here typically, here don't I? Anyway, the formula we had for that, which was super nice, was you take the gradient of f, you evaluate that thing at the point in question, you take the dot product with the unit vector, there's your rate of change, right? Or, if you like, you could express this as the magnitude of the gradient of f at the point P times the cosine of the angle, right? Where your gradient of f points in some direction, and your unit vector is some other direction. Theta is the angle between them. So the max and min rates of change happen for what? For theta equals to 0 or 180 degrees, right? And if you want to be constant at the point, you just put theta equal to 90, or let's say minus 90. Okay, okay, so what is that then? The gradient of f is, what we got here? We got y e to the xy minus 2y, oops, my bad, minus 2y plus x e to the xy, comma, 3z squared, right? Those are my partial derivatives. Now we want to calculate the gradient, this at the point, what, 0, 1, 2? So let's do that. We got 1 minus 2, 12, I believe. So that's your roadmap for calculating change in this function at that point, right? This gradient vector completely describes how the function's changing there, right? For example, is this a critical point? It is not, right? It's not a critical point because the gradient vector is non-zero. And let's see here. So to do it, my directional derivative then at the point in question, and let's say in the ABC direction. Let's let the unit vector be ABC for the sake of specificity. At the point 0, 1, 2. And did you guys double check me on this vector? Did I do it right? Okay, good. So we just got 1 minus 2, 12, dotted with ABC. So the formula for it, for what it's worth, would be like A minus 2B plus 12C. And of course, you could also write this as what? It's the magnitude, well, let's see here. What's the magnitude? So we have square root of what? 1 plus 4 plus 144 times the cosine of the angle between, this is the ABC vector, right? So what are the max min rates of change? Square root of 149 in the 1 minus 2, 12 direction, right? And the min rate of minus the square root of 149 in the minus 1 to minus 12 direction. Now, I'd be wrong for these answers if I had put language in the question which said, give me unit vectors in the direction of the minimum and maximum rate of change at the point, right? These would not be unit vectors. If I wanted unit vectors, I'd have to rescale these. I'd have to divide by the square root of 149, right? Yeah.
Isn't the gradient normal at that point?
Normal to what? I mean, that's a good question. That's actually a really good question. Let's ask that question. Let me write that question out. The gradient is normal to what? So can you guys tell me what is it normal to? It's in fact the normal vector field to something. Actually, it's the normal vector field to a lot of things. I don't know how to visualize them, but I can tell you what their equation is. So like there's a level surface, right? Level surface. The level surface, which I don't even know how to picture, but the equation of it is this: e to the xy plus z cubed minus y squared equals to a constant, right? This guy is normal to that surface. That's what it's normal to. So that's the surface, the solution set to that equation, right? That gives you a set of points on which the value of f is constant. And so if you want to move, if you move in the direction of the gradient, right, you're leveling up. You're moving off of that surface. If you move in minus the direction, you're leveling down. You're going to the lower level surfaces. But I think of these surfaces as like foliating all of 3 dimensions. There's like, it's something like a stack of, like a stack of sheets locally. Right? There's like f equals to C2, f equals to C1, f equals to C0, and the gradient of f is normal to these sheets at the point, and as you go in the normal direction, you're going up to the higher level surfaces. If we go perpendicular to the gradient of f, then we're going in a direction which is tangential to these level surfaces, right? Actually, this equation is actually not as bad as I was selling it. This is, in fact, a graph. This is a graph. So my picture is actually not that stupid. I say this is a graph because I can solve for z, right? Z is actually equal to, like, the cube root of c plus y squared minus e to the xy. So there you go. In fact, this level surface is a graph. It's a graph. I don't even know how to graph it, but it is a graph. I can write z as a function of x and y, and so as we run through different values of c, I think it'll move the surface sort of up or down with respect to the xy plane. So this is why it's good to have a review day in here, to try to like address these confusions, possible confusions between different parts of the course, because I mean, we have done more than one thing with a function of 3 variables, right? Like, we were not thinking about the geometry of a function of 3 variables when we did this stuff. We were just thinking about a point and calculating the change in the function at that one point, at that point in the course, right? We introduced the gradient vector long before we really discussed its full geometry. We discussed the geometry of the gradient vector much later when we talked about surfaces and normals and so forth. What if I asked the horrible question, characterize all tangent vectors which give you a rate of change of 4 for this function at the point? How would you describe that? What would you be up against? Rate of change. Let's do a couple different things. On the one hand, 20. On the other hand, 4 at the point. So you guys tell me. For 20, the answer is can't do, right? It's impossible because the max rate of change is the square root of 149, which is about 12.2-ish, right? It's between 144 and 169, which are the square roots of which are 12 and 13 respective. So it's between 12 and 13. Certainly we never get to 20. So this is impossible. Can't do. Impossible. Impossible. 20 is greater than the magnitude of the gradient of f at the point. Right? And since the directional derivative is based on a dot product, it is at most the magnitude, it's at most the product of the magnitudes of the vectors being dotted. But one of those vectors is a unit vector, and the other vector is the gradient. So the product of the magnitude is exactly the magnitude of the gradient vector. Now 4, this we can do. It's unpleasant, but here's what you do to get 4. You need to do 2 things. You need to solve a minus 2b plus 12c equals to 4. And what else? What's the other equation at play here? What's that? The unit sphere, right? This has to be a unit vector. So a squared plus b squared plus c squared equals to 1. So the common solution to both of those equations is the answer. And I'm pretty sure that's a circle. I mean, what's going on here is there's the unit sphere in ABC space. And this is a plane, right? In ABC space. And so like the solution set is some kind of like, it's some kind of circle on the unit sphere. There's a whole infinity of answers. Because basically you can take the normal vector, and if you have the gradient vectors in this direction, right? Then if you get a rate of change of 4 at angle theta off the normal vector, then it's still the same no matter where you are theta relative to the normal. You can rotate that theta all the way around. And as long as if you're like 30 degrees, for example, if your gradient vector point that way, if you just rotate that u vector around the gradient vector, there's an infinity of answer. You can kind of see how it's going to trace out a circle in the possible directions. But anyway, that's it. Questions? All right, let's try something else here. Let us calculate the flux. You're like, no! Can't we just pretend that's not on the final? No, it's definitely on the final. Hey, just be glad that I haven't structured the course this semester like I do sometimes, which is to not have a test 4 and to just have a final / test 4, which is more about vector calculus than the other stuff. That does seem kind of mean. in light of what's happened this semester. But you know, every Calculus 3 class struggles with the material at the end. But hopefully you get it, right? There's still time. All right, so where was I? Example 5. Let's look at the vector field f of x, y, z equal to, let's say, I don't know, 16x plus 6y plus 24z, just to take a random function, and then x squared, and then 3. Okay, there. So there's my vector field. All right, and I want to calculate the flux through the triangular surface. We found the equation of an example 1. Because a real problem that you might face on the final is like, here's 3 points in space, right? Or find a surface which contains those 3 points, and find the flux through the triangular region bounded by those 3 points on the surface, such that the normal point's in a particular direction, right? Like, that's a problem you might face. And we've already done the start of it, right? We've already found the equation for the plane. Once you do that, you should be able to parameterize the plane. So what's the parameterization? So I would suggest that we use x and y as parameters. X, y. What's my z? I go back to my example 1. I solve for z, right? Z is, let me see here, minus 1 over 24, 16 times x minus 3 plus 6y. That probably can be simplified. Right? Well, fine. You guys tell me how to simplify this for me. I've got x comma y comma what? 16 over 24 is what, 2/3? So I've got what, minus 2/3 x, and then plus 1/8. And what's 6 over 24? Minus 1/4 y, I believe.
There's a 16 in front of that.
Where did I lost my 16?
So it should be just 2. So 16 times x minus 3.
Oh, 16 times 3. Yeah, oh, thank you. So that's
Just turns into
40. Oh, that's a 2 then, right? I was about to say, I didn't seem like I have any fractions. And did I somehow lose the 16 in what else I did? No, that really is a 2/3, isn't it? That really is a 1/4. We could check it, right? Like, try it out. What happens if you put x equals to 0 and y equals to x equal to 0, y equal to 0? What do we get? X and y both 0. We get 0, 0, 2, which is what we're supposed to have. Right? 0, 0, 2 is a point. What happens when I put? Let's see here. When I put x and z both 0, what do I get then? So I guess that's a little bit trickier. If this is 0 and x is 0, what's that make y equal to? Y would be 8, right? Because 2 minus 8 over 4 is, if x is 0, it forces y to be 8, because 2 minus 2 has to be 0. So that's 0, 8, 0. Okay, it's fine. Just, I checked 2 points. Anyway, there's the parameterization. So what's the normal that's induced from this? So we do partial x cross partial x, partial y. And if you like, you could use r instead of the big X. As you know, I've used r in the past. I don't know why I've gotten on this kick of only using big X in your course, but it is what it is. 1, 0, minus 2/3, cross product with 0, 1, minus 1/4, which is, let's see here, beep, boop, bop, boop, 2/3, let's see here, 1, I think. Which, of course, you could write as 2/3. Well, excuse me, you could write that as 1/3 times 2, 2, 1. I must have made a mistake. What's that? 2, 2, 3. Is it, where's my mistake?
Isn't your y supposed to be 1/4, not 2/3?
You talking about here?
Yes.
So that 2/3 is wrong. It's supposed to be what?
1/4.
1/4? Let me check that. Oh, yeah, thank you. Minus 1/4? No. Let's see here. X hat across, yeah, but wait, yeah. 1/4. Oh, I should double check my dot product, right? So this dot that plus 2/3 minus 2/3, good. And let's see here. This dot that, 1/4 minus, okay, now they're with this is perpendicular to both, good, we're good. But more than that, you can, you should be able to see that, I mean, intuitively speaking, this got to be a scalar multiple of the vector that we know from the other problem, you know? Like this should be a multiple of my 16, 6, 24 vector, which I guess we could have written as what? 2 times 8, 3, 12. Let's see here, if I want to make, I guess I should just factor a 24 out of this. If I do 1/24, I should have like 16, 6, 24. I know that this has to happen because the normal vector is 16, 6, 24. So if I've got a 1 in this last spot and I want to make that into a 24, I just divide by 24. But I can't do it for just the z component in isolation. So it forces this calculation to make sense. I haven't checked it yet, but 16 over 24 is 2/3. 6 over 24 is 1/4. And of course, 24 over 24 is 1. So in fact, you can see that the normal vector field is in fact, not surprisingly, in the same direction as the normal that we found for the other problem. Unfortunately, I wish you could just assume that the normal vector was what you already know from like your previous work. It just doesn't quite work out that way, right? When you use x and y as parameters, that picks a specific length of the normal vector that corresponds to the partial derivatives with respect to x and y. I mean, there's an infinity of choices for the normal. There's only one, which is going to be the Cartesian product of x and y, of the parameterization of this thing written as a graph. That's unique. And the magnitude of that has to do with the area, which is covered by, if you look at a little dx and a little dy, change in your parameters. So anyway, my point here is we just calculated ds vector. ds vector is apparently, well, I don't know, you guys, what do you like? Do you like the 1/24 with the big numbers? Or do you like the, I like the 1/24 with the big numbers. But you could go with little numbers. It doesn't really matter. So there you go. There's your infinitesimal vector surface area element. What is the ds without the vector for this one? Well, let me just focus. We don't need to find that, right? So we're trying to calculate the flux of this vector field. So what's up next? I'm supposed to calculate f of x of xy. How's that go here? So I made this vector field up to be silly. This 16x plus 6y plus 24z, if we're on the surface, what equation defines the surface right here, right? 16x plus 6y plus 24z equals to what? What's that equal to? If you put the equation of the surface in, you get 48, right? So I know that if I plug the parameterization for this vector field, for the surface rather, into the vector field, this first thing will work out to 48. And you can try it. You can try plugging in. You can try plugging in the formula x of xy. You can plug in x for x, y for y, and put 24 times this, right? And maybe you can even see it. If we put 24 times this, and we subtract, we're adding 16x, and we're adding 6y, well then the 16x cancels, the 6y cancels, and you're just left with like, you're just left with the 3 times 16, which is the 48. Right. Anyway, so that works out to 48. On the other hand, what's next? X squared. What's x squared work out to when you plug in the parametric formulas here? It's kind of anticlimactic, but x squared is, well, x squared. And then there's 3. All right, so we're almost where we need to be. The flux then, and the question here would be, and I need a name. Let me just say it's the integral over, I'll call it omega, of 48 x squared 3 dot product with my ds vector, which in this case is 1/24, 16, 6, 24, dx dy. So I have the integral over omega. Let me be a little bit more cagey here. Leave myself some room to write stuff. So it's a double integral. Tell you what, I'll bring the 1/24 out front just to get it out of the way. And I've got, oh, no, you know what? I regret that. I'm going to use the 24 to simplify things. Good grief. So 24 divided by, 48 divided by 24 is 2. 2 times 16 is 32. So I got 32 plus x squared, 6 plus x squared over 4. I kind of regret not sticking with my fractions at this point. Oh well. And then plus 3, I believe. All of that, let's say, times dy dx. Then what's left to do? How do we actually set up this flux integral here? Like this down here is the omega, right? So to describe that, our x goes between, what is it, 3, 0, 0 here? So definitely the x bounds are going from 0 to 3. And the y bounds are tricky, but I see I've got 0 less than or equal to y less than or equal to whatever the equation is of this guy right here. Right, so that's when z is equal to 0. We've got 16x minus 3 plus 6y equals to 0 on that curve. So apparently my y is equal to minus 16 times x minus 3 divided by 6. So my bounds should go 0 to 16 over 6 is really just what, like 8/3, so like minus 8/3 x minus 3. And then we all know how to finish that. I just wanted to do the tricky part. I think setting up the bounds is the tricky part, right? A little bit. Are there ways to make this example harder? Sure. Do it in polar coordinates. Or maybe sphericals, right? Or use ellipsoidal coordinates, or maybe throw some hyperbolic cosines and sinus unnecessarily into the mix. Why not? Let's look at another example. Suppose, let's see here, example 6. You're given f of x, y, z equals to 10, and also f sub x of 0, 1, 3 is 9. F sub y of 0, 1, 3 is 0. F sub z, let me not make that 0, let me make it 10. F sub z of 0, 1, 3 is minus 42. All right, great. So calculate partial, let's say y, partial x, and partial y, partial z as 0, 1, 3. How do you do that? It's been a minute since we did this kind of chain rule. But let me just remind you that a simple way, there are two different ways to approach it. The one way is to approach it is to like just do just basic calculus 1 in context. You know, like just like this one, for instance. If I write this, this means that we must be actually calculating partial y, partial x, holding z fixed. It means x and z are independent. And y is actually a function of x and z in this context. If you're asked to calculate that partial derivative, it must be whatever cruel taskmaster has put you up to this feat, whether it's your thermodynamics professor or me, because we do these kind of partial derivatives in thermodynamics. But anyway, so the one kind of very boring way is you can take this equation and take the partial derivative with respect to x and say, well, that's equal to 0, because partial x of 10 is 0. And then by the multivariate chain rule, this is like partial f, partial x, partial x, partial x, plus partial f. Now you get really tired of writing these derivatives like this pretty quickly, right? So instead of writing that, we'll write like f sub x plus f sub y, partial x, plus f sub z, partial x, right? But to be fair here, what does it mean to say x and z are independent? What does that mean operationally? That's right. That means. Oh, okay. Thought that was me for a second there. So the last one's 0, which means, lo and behold, basically implicit differentiation, solve for partial y, partial x. It's actually equal to minus f sub x divided by f sub y, which for the given numerical data is, 10 over, oh my bad, 9 over 10, right? Minus 9 over 10. I personally think this is not the best way to do this calculation. It is a standard way. If you look at Stewart, this is how Stewart would tell you to do it. All right? So if you love Stewart for some reason, although he's dead, sorry, that happened. Just saying. Let's see here. On the other hand, better way, I think, is to just take the total differential of the equation. And so like fx dx plus fy dy plus fz dz is equal to 0. I take the total differential of the given equation, and this right here has a roadmap. This gives you the roadmap for finding all possible partial derivatives of x, y, z with respect to the other variables. And the rule is simply this. You solve for the dependent differential. So like if I'm calculating the y derivative, I just solve for dy. It's equal to minus fx over fy dx minus fz over fy dz. And from this, I can immediately read off that partial y, partial x is minus fx over fy, and partial y, partial z is minus fz over fy. And then, of course, I told you the numbers, so you can plug them in. Like, so like minus 9 over 10, like we derived just a second ago. And this one is, 42 over 10. So there you have it. I know it's been a little bit since we've done these kind of chain rule problems, but there is usually multivariate chain rule stuff on the final. That does happen typically. Let me also remind you an easy question about multivariate extremal stuff. Let's see here. Example 7. Suppose you have f of x, y, z equal to 10 minus x minus 2 squared minus 3y squared minus 10z squared. Okay, so plus dot dot dot. And then part B, you've got g of xy equal to 10 plus 3 times x minus pi plus y plus x minus pi squared plus x minus pi times y minus, y squared plus dot dot dot. So the question here is, so for part 1, for part A, my question is 2, 0, 0 critical point? If so, what type? And part B, my question again is let's say pi